Okay, I have to get going fast because we only have 2 lectures left. I wanted to reiterate, that since I decided the last two lectures would be just too close to the holidays, and I think many of you probably have plans, the exam will be early next week on Monday, and then we're canceling the last 2 lectures. Which means I have to hurry up with at least to cover most of the material. This is what I did last time. Concluded, remember the discussion on alpha and omega limit sets. I don't want to repeat completely, but both are tools to describe asymptotic behavior for trajectories. In brief, alpha limit sets and omega limit sets are connections of alpha limit points and omega limit points, and an omega limit point is in forward time a point that you as a trajectory will be revisiting arbitrarily closely as time goes to infinity, right? Alpha limit set is the same in backward time. We decided that alpha limit points or together form an alpha limit set for a trajectory, and it's really for a trajectory, not just for any short condition. It's associated with a trajectory, same for omega limit sets. These are the standard tools to describe asymptotic behavior qualitatively, even in n dimensions, although we are just discussing 2-dimensional systems. And the main result in this area, which is really a fantastic, beautiful result, is a general classification of potential alpha and omega limit sets in the case when, that's how I'm listed here, if a trajectory is bounded, okay? We had, prior to this theorem, we had a conclusion that if a trajectory is bounded, then say in both time directions, then its alpha and omega limit sets are non-empty, closed, connected, and invariant. That was a previous result here, okay? So when I assume now that the trajectory is bounded, which means in both time directions, then immediately have those properties, that the omega limit sets are not empty, closed, connected, and invariant. But what are they? And this theorem is an answer to that. That both of these limit sets must be one of the following: either a connected set of fixed points, which can be just a single fixed point that you keep visiting closer and closer, or a connected set of fixed points, okay? And I promised, I think, and never delivered on that, but I mean, a very easy to imagine possibility would be for that. As I mentioned, I'll give you an example, I think I forgot. Is just imagine a fluid flow in a box, a simple one actually, say laminar fluid flow, and if you have say no slip boundary conditions on the wall, that means that these are all wall points are actually fixed points for the fluid flow. They don't move, right? And then imagine that whatever you just have a simple circulation cell inside. So you would have trajectories like this, okay? And you see what's going on, right? Well, that's not, I would have to have a trajectory revisiting, you know, and getting arbitrarily close to these, but that's not a good example, sorry. Then it's not going to be a fluid example. I was too quick to say that, but I can imagine I can just create an example in which you have, say, a box of fixed points, okay? You make the vector field vanish on that set of fixed points, and you simply put, say, a source here and define a focus, so it starts doing this, okay? So that means that it gets arbitrarily close to the wall. It gets arbitrarily close to the wall, never intersects the wall, but gets closer and closer and closer, right? And that's not hard to manufacture in an example like this. You first, you know, create an unstable focus in the middle, and then you just introduce these invariant lines and make the velocity 0 on them, okay? Yeah, I had this idea from fluid mechanics, but then this would have to have strongly expanding flow to do that. So in 2 dimensions, in 3 dimensions, one could imagine with some stretching, but then you would have to keep coming back to this. So now that's a can of worms. Anyway, so this could be a case in which you don't just go to a particular fixed point, but your trajectory gets closer and closer to a whole set of fixed points. And in that case, the omega limit set would be, this would be the omega limit set, the whole wall box, right? Okay, so this would be then omega x naught for any x naught that you pick here. Okay, so that's one example. So that could be one thing. Note that it's connected, right? It's closed, it's invariant. It's actually not smooth, but the next type is smooth. It's a limit cycle. It cannot be two limit cycles or three, because the minute it was two limit cycles, then the omega limit set would be disconnected, right? And it has to be connected, right? So two limit cycles cannot be just a single one. And a set of fixed points and the connecting homoclinic or heteroclinic orbits, right? So this is a possibility. Of course, then the other parts may also be, may or may not be involved in that. Not necessarily. If you start from the inside, then you don't see that other part. You only see this kind of fish shape here. Okay, and at that point again, it's closed and connected, but not smooth. It's also invariant. Or it can be this one, a heteroclinic pair, say you're spiraling outside, or a finite combination of these. So finitely many fixed points and their homoclinic and heteroclinic kind of connections, and you may just be spiraling onto this like this. That's also possible. Okay, so this means that there's no complex or chaotic dynamics in two-dimensional autonomous systems, because this is, you see here the possible asymptotic behavior for boundary trajectories. And I also noted that this is also true on surfaces, two-dimensional surfaces, such as the cylinder and the sphere, because the topology of these is such, but not on surfaces with holes or handles on them. And one example was the torus, in which you can have a dense orbit, which is none of these types. Okay, so just a couple of remarks. Any questions on this? So one remark is that even though technically these are possible as limit sets, you won't see them too often. The reason is, in the general class of dynamical systems, these are not structurally stable. A connection like this, individual pieces of this picture are structurally stable. The stable and unstable manifolds are robust with respect to small perturbations, because the underlying hyperbolic fixed point is robust. But the fact that they meet exactly is not robust, because generally when you perturb a structure like this and you move the fixed point slightly, then they will miss each other. Okay, same for the heteroclinic connections. So homoclinic, even though they are theoretically possible, these connections are not robust. I'll just say that. Or I could say not structurally stable, which means that you will find arbitrarily closed dynamical systems that do not have these connections. So we do not expect to see them, although they are in principle possible limit sets. Okay. So what happens to them, this is just a little sketch, that even if you have them in a parameterized family of systems, okay, then you have some sort of a perturbation to that system, even small, then they may, the fixed point itself is robust. It's a hyperbolic fixed point with stable and unstable manifolds, so there's going to be a nearby one. But generally speaking, these will miss each other. Okay. Also the same for a heteroclinic connection. Okay, so you may have it, and after a perturbation, what actually happens a lot is that, again, the individual hyperbolic fixed points are robust, so there will be nearby ones, but there's no reason why the stable and unstable manifolds would coincide. So I'm just drawing one possible scenario which happens quite a bit. So this comes like this, goes like that. This comes in, this goes out. So possibility is this, just spiral in, this keeps going. I'm not saying this is the only way they can break, but this is one way, fairly typical. Okay. However, within the class of conservative systems, it's a bit of a different story. Within the class of autonomous planar, because we're still talking about 2D systems, so systems that have a conserved quantity, homoclinic orbits are structurally stable. I mean, modulo degenerate cases, but you know, whenever this is a hyperbolic fixed point, it doesn't just look like a hyperbolic fixed point, okay? But really, when you linearize, you don't get zero eigenvalues. But so these are not non-linearly stable and non-stable directions, but rather linearly stable directions. So this is just a hyperbolic fixed point. The homoclinic orbits are structurally stable. I'll just add for hyperbolic fixed points, because you can technically have a homoclinic orbit to a non-hyperbolic fixed point as well. And then there's no reason why they would, you know, they would break. So the reason for that, I'll just give you a sketch. Remember the little sketch that we had in terms of for the potential for a system like this, mx double dot plus dv dx, the potential that only depended on x equals 0. So it was the potential that mattered. And I keep writing partial with respect to x, and I don't have a good explanation why, because that's the only variable there. So I just write v dot x equals 0. And for a homoclinic orbit, remember, you have to have such a graph for v. That's the geometry that gives rise to homoclinic orbit. The way that comes about is that you draw this energy level, right? And then you project it down to the phase space, of which you have a copy down here. That was the procedure. So this is x1 and x2. Remember what the x1 and x2 coordinates were, right? So x1 is just x and x2 is just x dot, position and velocity. And the procedure was to project it down here. So there was one equilibrium here. There was another equilibrium here. There was a turning point there. And you turn back there. When we talk about a general dissipative system, there's no such structure behind. There's no potential or anything. It just happens that for a particular set of parameter values, you get a connection, right? But for a conservative orbit, a conservative one-dimensional, one-degree of freedom system, there's an underlying potential, or generally speaking, conserved quantity, but in this case, potential there. Now, what happens when you perturb that system? When you perturb that system and still within the class of conservative systems, then what you're essentially doing, you're deforming the potential slightly. So maybe it becomes something like that. You know, the main topology, I don't just mean you're shifting it, there's deformation in it. So maybe my plot is a bit misleading. I don't just mean you simply shift it, but you know, maybe you do something like that. But the point is now that if you then have this new equilibrium point, which is somewhere, the new maximum is somewhere here, okay? And your new minimum is somewhere there, and your new turning point is somewhere there. Okay, I'm blowing this up. Then when you redraw the figure under these new conditions, so this is now, these are now the two fixed points, and there you see the turning point, then your picture will be something like that. So there will be a nearby homoclinic orbit. So this is a persisting homoclinic orbit. So that's something to keep in mind. So Why? Because this is just a small topological deformation on a curve, and that will not change the fact that locally you will have a nearby maximum. In fact, that's, you can work that out, implicit function theorem. Not change the fact that you will have a nearby minimum, right? And the overall thing that there was a non-existence of a fixed point here, also under small perturbations, that that doesn't change. So overall, you will have an upward moving potential, and that's all you need geometrically for a homoclinic orbit. Okay, that's why, in fact, in conservative systems, this is a very, very typical phenomenon. You see it a lot, whereas don't expect to see it in some others. And that's also sort of a message that if you see it in a model, you have to ask yourself the question, am I just picking very specific parameter values perhaps, and what I'm seeing is non-generic because I should not be seeing it, or maybe there's a symmetry, maybe the conservation law in the model that I have overlooked. At the same time, I cannot extend the same conclusion to heteroclinic orbits. That's also something to keep in mind. They are equally unlikely in conservative systems unless you have an additional symmetry. Okay, and the reason for that is that if I now draw the similar graph to conservative systems, I'm sorry, no, that's all in the conservative setting, but now I assume that I have a heteroclinic orbit, which means that the potential has to have, whatever it does, it has to have two maxima of equal height. So they have to be on the same energy level, which is not the case here, but something like that, right? So when I project these down, then down there, I will get before perturbation, I will get a heteroclinic connection. We've done this. So here you have the two fixed points. There's one in between, right? And here's your connection. Except that it's nicer. I should be able to hit this. Something like that, okay? Now imagine perturbing this curve. So when I do now the green curve, yes, I will stay nearby, no question, small perturbation, whatever. And I will stay nearby all the way. That doesn't change. But who's to say that unless you have some really special symmetry, who's to say that those two peaks will be on the same energy level, even after perturbation? Generally speaking, unless something constrains them to be, okay, this will be one energy level here for the first peak, which I have a hard time drawing. And this is another energy level for the other peak. So this will be V1 and this will be V2, and generally V1 is not equal to V2 generically. So unless you have a symmetry. This is a grammatically not a correct sentence, unless symmetry, but hopefully you understand what I mean. So that means that, then let me blow this up. When you then perturb this point, it will land somewhere here, and the other point will land somewhere there. Okay, and one of them will be higher than the other. In my picture, this happens to be higher than the other. So basically, I will have a homoclinic orbit developing in this direction. So between this point and that point, now I have a perturbed homoclinic orbit. And this perturbed point, the upper point here, is still a maximum, so it will have a saddle type dynamics, but that energy is locally not bumping into anything here, so it will have an open geometry. It's a bit my drawing is a bit tight here. Maybe I use a different color to make sure we see the difference between the two. So the other one, so suppose that's here, right? So I draw the corresponding curves. They will respect that nearby homoclinic orbit, but generally pass by. So if you happen to have a heteroclinic orbit, then you perturb that configuration, then it usually breaks into homoclinics. Incidentally, that's the reason somebody gives you a streamlined plot from a general two-dimensional flow, or you just look at a map, which is level curves of a function. You shouldn't be seeing heteroclinic connections in a generic picture. And indeed, you look at streamline plots. Why? Because in the case of streamlines, the stream surface instantaneously acts as a conserved quantity along those. And you should be, we always, I mean, no matter how complicated the flow is, I mean, one sees these all the time, or the type of closed orbit, saddle points, homoclinic orbits too, because they are robust. But somebody gives you an instantaneous streamline plot of a non-symmetric fluid, you should not see heteroclinic connections in general. If somebody has the power to change parameters in that flow, then maybe for one parameter, but after that it breaks. Unless the system is symmetric, and you could say, wait a minute, I see this in the pendulum. Yes, we see it in the pendulum, and presumably I also see it if I start tinkering with the parameters of the pendulum. I change the mass, change the length. Sure, I always get the same thing. Why? Why is it then robust? Because I have a symmetry. No matter what I do with the pendulum, unless I really start breaking the symmetry, it has an inherent a symmetry that after a while the coordinates keep repeating themselves, right? With period S1, because that's physically a cyclic coordinate, which means that I'm coming from this direction, coming from that direction, the energy level should be the same because it's physically, those 2 points are physically the same. So if I perturb the potential for one of them, then automatically I'm perturbing the potential for the other one because they are physically the same. That's why if you start tinkering with the pendulum and you're bumping it here, that's fine, but the exact mirror bump will appear there. That's why it's robust with respect to the pendulum, but not in general systems. Okay, so that's one remark. And the other remark is some consequences of the Poincarè Bendixson theorem, some immediate ones. So this is one consequence. So that's not just a theorem, this is a theory, because it's a complete classification of the possible alpha limit sets. And that's the following. Let me just spell it out first and then do a picture. If you have a forward invariant, which means that you might be backing out of it, but in forward time you're stuck in it. Forward invariant bounded open set without a fixed point. So you know that there's no fixed point in it. Must contain a limit cycle. So if you have, say, a region like this, I'm giving you one example, just say a ring type region, and you find that at the boundary, the vector field points inwards, and this can be of general shape. And what I'm drawing here, you can verify that. Even all you need to do is just verify an inner product between, say, the boundary normal and the vector field, and it has to be negative strictly, right? The boundary normal points outwards, and the vector field has to have a negative inner product with that. If it's strictly negative, then it's an inflowing boundary. The same here is one of those situations. So you're getting into what's a bounded set. You cannot get out of it. So that means that your forward behavior is necessarily bounded, which means that the omega limit set of any trajectory here is non-empty. The minute we have that, we know that it can be only of 3 types, either a set of fixed points or a limit cycle or fixed points connected by these homoclinic or heteroclinic orbits. But I have just assumed that there's no fixed points. So that knocks out the first possibility and the third possibility. Is it too much to assume? No, because in 2 dimensions, also in any dimensions, I mean, finding fixed points is an algebraic problem. in MATLAB, there's a command. If your vector field is defined by two functions, you can ask for the joint zero level set of those, right? And that would automatically then look for the fixed points of those. And so that's an algebraic problem that doesn't require the solution of differential equations. It's not that hard to do. So if you can exclude the existence of fixed points, then you have already knocked out the first type of limit set in Poincaré Bendixson. So this cannot be the case, right? This cannot be the case either, because yes, it's got these fancy things that you a priori cannot rule out, the heteroclinic and homoclinic orbits, but they're always connected to fixed points and you don't have any of them, right? And you can't have them on the boundary either, because it's an open set and along the boundary, everything points strictly inwards. There's no fixed point on the boundary either. So your only bet is a single limit cycle, right? Now, in principle, does it have to be that's a good question. I said, no, let's say a single limit cycle for a given trajectory, but can I have multiple limit cycles within that? Any guesses? So maybe, you know, I can have one here. We agreed on that, right? And of course, what that would mean is that at some point these trajectories have to turn, right, and pick up the limit cycle. Can I have more? Well, this is then presumably stable. If I just have another one, which is unstable, okay, so it keeps pushing trajectories away, that somehow doesn't square with the fact, well, that the trajectories are coming in, but I could have three. So I could have a stable one outside, then I could have an unstable one in between, and I could have another stable one. So everybody who's coming in here is wrapping on the smaller stable one. Between the two, this stable and that stable, I would have an unstable one, and then I would have this outer one. So I could certainly have more than one, but I have at least one. Now, does that violate anything when in relation to what I said about not being able to have more than one limit cycle in an omega limit set? No, because that's for the omega limit set of one particular trajectory. Okay, so one particular trajectory that comes in certainly won't be able to converge to three limit cycles. For that one, this is the omega limit set. But for the others, say who are coming in here, there will be another one. So individually, each and every trajectory can have no more than one limit cycle as an omega limit set, but there can be several coexisting omega limit sets. So the statement is that inside this, there exists a limit cycle. And that means not necessarily one, but there exists one. And that's the statement. Okay, so that's kind of a quick condition and pretty powerful if you think about it, because all you check is the existence of equilibria, and based on the non-existence of equilibria and the basic geometry of the phase portrait, you can reach a pretty powerful conclusion. Okay, and then I'll just add that possibly more. Okay. Now there's another one, there's a famous consequence, which is a pretty nice analytic criterion that also has then mechanical implications or physical implications that I'll tell you about. And that also has Bendixson's name in it, and this is called the Bendixson criterion. There are many other criteria actually for existence and non-existence of limit cycles, but this is perhaps the most classical one and the easiest to explain, and there are more involved ones. So the Bendixson criterion deals with two-dimensional autonomous dynamical systems, which we have been looking at. So they are on the plane, okay? And let's just assume that we do need at least one continuous differential probability for this proof to work. So normally we just assume C1 out of convenience. But for this proof that I'm giving you, I'll give you a short proof. We do need one's continuously differentiable. Okay, and there's an assumption. That's the single assumption beyond the continuous differentiability. So assume that on this set on which I'm looking at the ODE. So no, sorry, I'm I'm just writing too much. I should have written it here. So I consider this to be on some U domain, and I restrict the U, right? And it's not, generally speaking, R2, because even though the equation might be defined on the whole of R2, but the property that I'm going to assume now, I only assume that on a set U, and U is simply connected. Okay, which means that if you draw any circle within U, any circle, any closed curve, then its interior is also contained in U. So there are no holes in U. That's the simply connected, I remind you. So assume that when you take the divergence of this F, so if you're not used to that notation, just write div F, then that's non-zero on U. Okay, so which means, I mean, generally speaking, you have a function, then why would it have the same sign for the divergence? But let's just assume that you're able to isolate, you're able to identify a simply connected region of the two-dimensional domain of definition of the system in which the divergence has the same sign and it's non-zero. Okay, then the statement is, then there exists no limit cycle for the system entirely lying, I'll just say entirely contained in U. So you may have limit cycles, but they must leave U. So if you are able to pick this U fairly large for your purposes, the domain of interest, then you're finding that you have been able to pick a simply connected U in which the divergence of the system has constant sign. It doesn't have to be constant sign. There's no way you can have a limit cycle there. Okay, and that can be a pretty strong result, and it has, you know, I've seen more than one case in which this was really rendering very important physical conclusions because it's very easy to verify. Right. So I'll give you a little proof because it's kind of nice. So there are other proofs, but this one is somewhat heuristic, is simple. So if you simply look at the F perp, which is the vector field which is normal to F, and one way to generate a vector field like that, as you know, is you switch the coordinates of F in some coordinate system that you have, and you add a minus sign to one of them. So if F was originally F1 and F2, okay, then if I consider F2 minus F1, then clearly that's normal to F. Okay. Then with the help of that vector field, if I consider this integral, then assuming the contrary first. So there exists a limit cycle. Doesn't matter if it's stable or unstable. Gamma entirely in U. Okay. The consequence is that if you then take the integral over gamma of the quantity, so that's a closed integral of the vector field F perp, which is a vector dr. Okay, then if you parameterize that using the trajectory on gamma, so here's gamma as an object. This is gamma, but at the same time, you can just pick an individual solution running on gamma x of s, okay, which is the same as x of s plus some capital T. Why am I using s? I should be using time. I can't tell you, so that this is x t plus t for some capital T, okay? So I use that solution to parameterize this line integral. And then what it translates to is f perp. And then dr is x dot dt. And then I have an inner product here. I already had an inner product there, but I didn't write it down. Okay. Now x dot is f of x. So this is just the integral from 0 to t f perp dot f dt, and that's 0. Because f perp was constructed at each and every point to be orthogonal to f, and therefore along the limit cycle, it's also at each and every point orthogonal to f. Okay, so for that reason, this is pointwise 0. So therefore that integral is 0. Okay. Now at the same time, I can also try to evaluate that integral in a more complicated fashion. So if I write down this integral and I use the appropriate version of Stokes' theorem on the plane, which usually goes by the name of Green's theorem, but it's really Stokes' theorem. It says that you can transform this with the appropriate orientation. If it's clockwise, I think you can transfer this into an area integral over the interior of gamma. What you need to do, but it works out to be Stokes' theorem in the plane, is that you need to take the curl of f perp, which it's gonna be a vector like vorticity for planar flows, normal to the plane. It will have only one non-zero component, and you take that. That's the one I refer to as 3, or the z component. Okay, and you take the area integral of that. So to write out what that is, so it's like the vorticity of the curl of a planar vector field. So it goes like this: you take the f perp second component and differentiate with respect to your first coordinate component, whatever that was, when we defined x here. Then I can just use those coordinates. It's the same coordinates with respect to which I'm already using f1 and f2. So that, and then I have to subtract the partial of f perp 1 with respect to x2. But if I now remember what the perp variables were here, okay, so f perp 2 was just minus f1, and f perp 1 was f2. Plug those in here, then what you will find that this is the partial of f1 with respect to x1 minus the partial of f2 with respect to x2, and that's just minus the divergence of f. So when I plug that in here, I'll just rewrite that. I'll pull out the minus, and I have this area integral over the interior of gamma of the gradient of divergence of f dA. And now look at my assumption. The assumption is that this divergence is non-zero. Whatever it is, I don't know what it is, it's certainly not constant, but if it's non-zero on U, and this interior of gamma, which is here, right, and which is definitely somewhere inside U, and this is the interior of gamma, fully in U, where this assumption holds. So therefore, this function has a constant sign over that, which is non-zero at each and every point. So when I then integrate that of the same sign, of that function of the same sign, then definitely this is non-zero, right? Because at each and every point, the function is non-zero and has the same sign by assumption. And that just comes from this assumption. let's call it star. So that's the star, the implication of the star assumption. But then I have a contradiction, right? Because on the one hand, I got that this integral is 0. And on the other hand, I got that it's strictly non-zero, right? And the reason for that is that I assumed the contrary of the statement, okay? So that by contradiction, I have proven that this is, then we're done. So this is something quite easy then to check, right, in applications. And you could argue that this is not a positive statement because it's not about the existence of a limit cycle. If the divergence of f vanishes on you, it doesn't guarantee that it has a limit cycle. So it just basically helps you identify regions when you suspect that there might be a limit cycle here. It helps you exclude regions as a possible explanation. Limit cycles in certain regions are possible explanation for something, right? And you may still have a limit cycle in you, I'm sorry, in general, but it has to leave that domain, okay? So it cannot be fully contained in you, right? So what I've drawn here is not possible, but this could still be possible. There's nothing against that, okay? So one implication, any questions on the statement? So one that I think is important, and I've seen people overlook this. That's why I think it's important. I sometimes even people, you know, in mechanics articles and talks, and they kind of forget about this, or maybe I've never really thought this through. So a consequence of the Bendixson criterion first, I spell it out, and I would just say, I think it's an important one, is that generally speaking, purely damped or purely forced perturbations of conservative systems cannot have limit cycles. And note that there's no more any u in this. Of course, then I have to say what I mean by these notions. Okay, so let's see what I mean by that. Is that, again, this is all 1 degree of freedom, right? Don't apply this to higher degree of freedom problems. But if you have a high dimensional system that you manage to reduce to a lower dimensional set, so if a reduced order model, of course, then it applies, okay, to that. A lot of systems can actually will have a 1-dimensional core, so to speak, okay? So it's not that you will never face this situation. Just today, I had a research update with one of my students who works on data-driven modeling of high-dimensional systems, and you know, he got it down to a 1 degree of freedom problem, and he was using the Bendixson criterion. That's an interesting coincidence to show me, unfortunately, that what I was speculating about is not true. But I was very proud that he remembered the Bendixson criterion for nonlinear dynamics 1, and when last time I suggested something, he went back, thought about it, came back and said, no, what you're proposing is not possible because the Bendixson criterion, in fact, exclude that. So I was very happy to be wrong. Anyway, but it comes out in unexpected situations that even, you know, data-driven modeling of high-dimensional systems. Anyway, so what is this then? So let's assume that you have mx double dot, and then you have the partial, which I love, which is not really a partial, v prime of x. So far, this is a 1 degree of freedom conservative system, right? The ones we've been talking about. And now I say that this is subject to some forcing. So and this will be the non-conservative part. And that can depend on position and also depends on x dot. And the beauty of the thing is that when I say perturbation, I usually mean its norm is small, some norm. But in this case, I don't mean that. It can be actually arbitrarily large. So G is possibly large, is potentially large even. No bound on the norm. And when I say potentially, that has nothing to do with V. That's a different potential. Okay. So what is the one degree of freedom, the first order formulation that we often find advantageous to work with? And you know, for me to apply the Poincaré Bendixson in any way, I need to pass to a first order form, because this is not stated for a second order equation. It's stated in the first order form. So what's the first order formulation? So as usual, we say x1 is just x, right? And x2 is x dot. So as a result, I have x1 dot equals x2, and x2 dot, which is x1 double dot. So I have to divide by the mass to get to it, will be v prime x1, right? So this would be the conservative part. But now I also have this additional, and I forgot the 1 over m, 1 over m g x1, x2. So this is what my perturbed system looks like. I've added, you know, this covers a lot of ground. And I'm not saying that the G is small. So essentially, you know, any 1 degree of freedom mechanical system that has a well identifiable part, which is, you know, conservative, which means potential, and all the rest is here. And I'm not saying it's small. And if I want to then start working on and potentially, you know, exclude the existence of limit cycles, then what I've learned from Poincaré Bendixson is I need to, it's a good idea to take the divergence of the right-hand side. Now, what's the right-hand side? The right-hand side is this whole function f, right? f1 and f2. So then the divergence of the right-hand side will be what? Well, I have to take the first component differentiated with respect to x1, but that's 0. Then I have to take the second component and differentiate with respect to x2. So the potential part gives me 0 because it doesn't depend on x2. And I only get non-zero if g depends on x2, which means that I have a dependence on velocities, okay? Which actually not unexpected, because if you don't have any dependence on velocities in this function, then I can just subsume that into the potential, because it only depends on the position. So I can just look at its antiderivative in 1 dimensions, but integrate g and add that to the potential, and I'm done. So I'm still in the conservative framework, right? So in fact, for this, in 1 degree of freedom, 1 degrees of freedom, for a system to be non-conservative, to have no conserved energy, so not to be of the type kinetic plus potential, I absolutely have to have an explicit dependence on x dot. Otherwise, I can just subsume that, integrate g, and that will be part of the potential. Okay, so I have to have that. Otherwise, I wouldn't call this non-conservative. So that the divergence will be only the partial derivative of g with respect to x2. And here's when I define what I mean by purely forced or purely damped system. So when this, I find that this is larger than 0, okay? This derivative is larger than 0, then I will call it purely forced. I find it's less than 0, I'm making it purely damped. This will be my definition. So it's not so much the sign of g, but it's the nature, the way it depends on the velocities. And the immediate conclusion is that now imagine that on the whole plane, or at least on the domain of interest, no matter how large it is, it's either purely forced or purely damped. That means that the divergence never hits 0, it has a constant sign. So it doesn't matter what you pick for u, you will always be in a situation that you are satisfying the assumption of the Poincaré Bendixson theorem. So for any choice of u, you cannot have a limit cycle in U, right? So the conclusion is that by the Bendixson criterion, there exists no limit cycle in U for any choice of U. Let's a bit more specific. If I now consider a completely general mechanical system, say badly nonlinear, very complicated potential, and what I'm adding to it is in fact what we customarily write even before this, which is kx dot, which is linear damping, but arbitrarily bad nonlinearity. Okay. Then what is my gxx dot? So in that case, my gxx dot is minus, because I have to put this on the other, put on the other side, minus k times x dot, right? Because the way I was discussing this, the additional force was on the right-hand side. So take this damping force, linear damping, and put it on the other side. So this is my G. Mind you, however, now this is not a conservative system anymore, and I'm not even saying that K is small. This can be pretty large damping, and I'm not saying anything about the potential. It can be pretty bad, you know, with lots of ups and downs, right? Very strongly nonlinear. So I know very little about this system, in fact, okay? Now let's check whether it's in the purely forced or purely damped category. And I should just put that this is my definition for this purpose. Let's take remember what I need to take. I need to take dg dx dot, because that's what it is with respect to the second coordinate. That's just minus k, right? And no matter where you are in the plane, minus k is less than 0. So for any choice of U globally in the plane, there's no way that you can pick any set that contains a limit cycle, right? So no limit cycle. And people sometimes forget this, and then because the equilibrium, see the equilibrium point, which this system has, say at x equals 0, can easily be, I already said bifurcating, it can easily change the stability time from a center to a focus, stable, unstable focus when you add k. So it can really happen. So when you plot the eigenvalues, so the eigenvalues at a fixed point, what should I like? That is, well, this is lengthy. That is a potential energy minimum for, it's a complicated way. So when, suppose I, you know, cross out the damping for a second and then remember the plots, if the potential energy has a minimum, then that's a center, remember, downstairs. So right there at k equals 0, you will have a pair of eigenvalues for such systems here. So this is the k equals 0 case. And what I'm showing here is the real part of the eigenvalues, and this is the imaginary part. So for all these systems, when you have potential energy minimum, then your eigenvalues reside here. And when you turn on the damping, and the damping is small, then these will invariably, the centers will always be perturbed into stable foci. When you then increase k further, you may change the focus into a node, which is an overdamped system, but initially it's always an underdamped system. So as you turn on epsilon, or on k, you're actually crossing this axis like this with a non-zero speed. because when k is negative, then it's in fact a self-excited system. It turns into forcing, so it makes the center, turns that into an unstable focus. So you're definitely crossing it. And I've seen papers in which people conclude that, hey, this derivative is non-zero. The real part, what was that derivative? Remember, for the Hopf bifurcation that one needs to look at is the real part of lambda j divided by k, which is also the bifurcation parameter here. So at k equals 0 is definitely non-zero. And people say, okay, so Hopf bifurcation, no way, we have just concluded. So in what way is that possible? Because if we scroll back to the Hopf bifurcation conditions, which we had someplace here, where did I have those? At the bifurcation. Yeah, here, remember that? We had people say, oh, this is satisfied, we're done. No, here comes the second condition. You also need to check this one. And what was that A naught? That A naught was the first non-trivial term in the normal form of a system. Here in a planar system, we don't have to reduce the center manifold. So you already just do because you are already on the center manifold and you have a center on the plane. And remember that this A naught was tied to the limit of the system, which was the system at k equals 0 at criticality. So in our current case, if you were to then do this calculation and calculate this normal form, which is still valid at that point, then you would calculate this A naught from the conservative limit. If this came out to be anything other than non-zero, then you would have a contradiction, because some value of k, for some value of k, either supercritical or subcritical, you would be getting a periodic orbit, because the statement was that what you get from this truncated normal form is locally topologically equivalent to the full system. So we would be in contradiction in any way, either for positive k or negative k, if this was non-zero. So the only resolution of that is that this must be 0. There's other ways of proving it, but I already mentioned it then for conservative systems, this must be 0. And now this is what I have just shown you is for perturbations of conservative systems. So when you compute this for a conservative system is 0. And what I have just shown you is a proof of that, because otherwise we would get a contradiction. So we already established that even though, excuse my scrolling, the first condition of a Hopf bifurcation at k equals 0 is satisfied at the center, but the second condition must necessarily fail because there cannot be any limit cycle. Okay, so let me just, the first condition is satisfied, yet we cannot have any limit cycle for k non-zero. I mean, I was dwelling on the case when it's less than 0. But if you then switch k back to on this side, this is the relevant side. When I turn on k, I think I did the arrow in the wrong direction. Please excuse me. I have to, because when I turn on the damping, and in fact, I'm crossing in the other direction. So when I turn on the damping, I'm going in this direction because the system becomes damped. So this is the k bigger than 0 case. And this is the k less than 0 case. When k is less than 0, then, which means minus k is actually bigger than 0, then I'm introducing pure forcing to the system. So it would be like a negative feedback loop. You can think of this term then as a control term that is a negative feedback based on the velocity. When k is positive, just think of it as damping. Okay. In either case, the result kicks in. Because this term then has a constant sign, which is non-zero. Okay, so in either case, in either side of this story, you cannot have any limit cycle. So no subcritical Hopf, no supercritical Hopf, right? And the only, so since we cannot have that, the result is that A naught must be 0 in the Hopf normal form. And that's a property of the conservative system because it was the leading order cubic nonlinearity in the normal form. And this is true for any one degree of freedom conservative system. And the reason I'm emphasizing, I've seen people forget that at all levels, starting from student to professor and whatnot, including myself, actually. Not these days, but in fact, during my master's thesis, I was embarking on a calculation that I was hoping it would lead to a Hopf bifurcation or a periodic orbit. And my professor at the time, who was supervising me, who was very knowledgeable, was pointed out that no, that would actually violate. I think he may have phrased it in terms of conservation of energy, but Poincarè Bendixson. So then I learned that lesson for life, right? Because it would have been a very expensive calculation, and he was able to tell me immediately that it would lead nowhere. So anyway, that's easy to forget. And I think that's what I wanted to say about maybe planar systems in general. Any questions on this?
I have a quick comment.
Yeah.
I think there is an example of an external forcing which is only position dependent and still non-conservative, which is a follower force.
Say it again, excuse me.
A follower force. So I remember studying a course of stability of structures for a cantilever, for instance. If it is subjected to a compressive load and this load follows the axis of the beam, then this is a follower force, and I think this is path dependent.
Yeah, but that only works for higher degrees of freedom. In 1 degree of freedom, what I've said is always true. When you have a follower force type problem, the matrix of that, in multi-degree of freedom problems, this is not so trivial, because if I write down a vector field, it's not necessarily a gradient vector field. Okay, so you may not, just because something depends on the position, it doesn't mean it derives from a potential. But in 1 degree of freedom, when we're talking about a single variable potential, it's always true. So what you're making is a good point, but so my statement would not be true in 2 degrees of freedom or higher. But in 1 degree of freedom, it is true.
Yeah. Okay.
Okay. So hopefully the example you've seen has at least 2 degrees of freedom.
Yeah, it was a beam. It was 11 degrees of freedom.
Okay. But you see the reason why, because I can always take a position-dependent function, and in 1 degree of freedom, as long as that's a reasonable function, say continuous, it's always the derivative of something. So any function, and it derives from a potential if the dependence is always spatial. That's by no means the case in 2 degree of freedom. When you ask, you have a vector field depends on space, does it derive from a potential? And then it actually, there's a condition for that it has to have a vanishing curl to derive from a potential, right? So there are restrictions, and that's why the follower force example works. And you're right. Yeah. Anything else? Okay, let's move on to the last section, which I then want to finish next time, which is time-dependent dynamical systems. And usually this is my prelude to a little bit of chaos in the course, but I think the chaos will be then discussed in part 2 now. I always discussed chaos in more detail in part 2, but sometimes I get to the point that I can even discuss some of it here. So, but I need this section here, and it's of course independently of interest, time-dependent dynamical systems, so which is basically non-autonomous dynamical systems. That's the equivalent term, which really we haven't really talked about, except at the beginning, where basic theorems are stated. Okay, so the general form we're looking at is this no dimensional restriction a priori, although pretty soon I will have to restrict things. So like I said, this is a non-autonomous dynamical system, and there's not much I can say about this beyond the initial theorems that I have listed, you know, existence, uniqueness, dependence on initial conditions, and all that, right, that we discussed. Now, let's actually now look at the subclass of systems is non-autonomous linear systems. So that's our first subject. So you would have then some time-dependent matrix multiplying X, and there's an inhomogeneous term there. So A is for any fixed T is an M by N matrix. This is sloppy, I know, because this is a function of time. So this would be a mapping, you know, okay, which I want to avoid. So I just write A of T for any T is just an M by N matrix. Okay, and the B of T for any T is an n-dimensional vector, and I will assume that these are nice in the sense that at least continuous, because for the fundamental theorems, you might remember that the dependence on time doesn't have to be that great. It's enough if it's continuous. The dependence on space is already super nice for any linear system. This is C infinity, analytic, so you know, it's a whole lot more than Lipschitz. If these are reasonable functions, so that I can be generous and only require these for now to be continuous. I don't need more than that. Okay. And the homogeneous part of the system sometimes is the only system, and there's no inhomogeneous part, is X dot equals AT of X. This generally will have global existence. In fact, I think this was one of my examples where I showed you that you can give an estimate that this always, solutions of this, as long as A of T is integrable, there was an estimate that I did earlier, then this will always, solutions of this will not blow up. So you can always continue them. That was one, I think, one instance in which we were talking about these systems. But the general solution structure of these systems is that it has a fundamental solution matrix, which at some point, I think I was not here then, and maybe Shobit covered it when we were talking about linear systems. I don't remember covering it, but there's a fundamental solution matrix, let's call it phi, defined between T naught and T, and that acts on X naught. And this fundamental solution matrix between T naught is T, when you evaluate it at T naught, is the identity. Okay, so the nice thing about linear systems is their solution evolves under a time-dependent linear operator. This is really just, I don't have to write this because this will have a matrix representation, but it's a linear operator acting on the initial condition, moving it forward. Okay, and it has nice group properties that at the time we discussed. So they form a group. These. And when the system is autonomous, then we also have a fundamental matrix solution, except that we know what it is in that case. It's e to the AT. Fundamental misunderstanding or mistake or superstition or whatever is that even for time-dependent systems, you can write down the exact solution in an exponential form. And that, again, there's a lot of believers of that assumption or theorem, but it's not the case, and that's very, very important to be aware of. So generally, please remember that. In fact, as a rule, when if you're interested in this fundamental matrix solution, it's not what you think or you would think if you have not, maybe you have some memories from linear systems. This is not, as many would guess, the integral from T naught to T as ds. And the reason why many guess that, because you may start following the same proof that you would be using to show that when the system is autonomous, then it's simply e to the e times t minus t naught. And if you're not careful, you might even think that, yeah, the same proof goes through. But there's a point in that proof where you actually use the fact that A would use here is that A would have to commute with its integral. And generally speaking, that's not the case. If A of t commutes with its antiderivative, with its integral, then you can actually show that it's still the case. And then this is the right way. But that's very rare. Okay, it's a very strict constraint. So I would say unless, and this is the thing to remember. So this should be your guiding rule, because the unless is a very rare case, unless you have, A of t commutes with, say, the integral from t to t as ds, which generally speaking will, these have very little to do with each other. There are notable cases in which that is true. So say when you have a two-dimensional matrix, which is diagonal, but that's not such a interesting case, right? Because if the system is diagonal, then this is just two decoupled set of scalar differential equations, right? Which you can individually solve, right? There's perhaps another case which is less obvious because you don't have the decoupling. It's when this matrix is still two-dimensional and skew symmetric. Then you can show that this is again the case. So you can exponentiate this and integrate it. It will be the right. But these are pretty much the only examples that I can give you right offhand when you try to do this even in higher dimensions. I mean, this would work in any dimension because a diagonal matrix always decouples this into individual scalar equations, which you can solve. But if you go even for a higher dimensional version of that, this is no longer the case in 3 dimensions anymore, that A would commute with its antiderivative. So this is really restricted to 2D. Okay, so this would generalize to any dimension, diagonal matrix, but this one wouldn't. Okay, so this is just these are just in parentheses. The reason why I'm emphasizing that is, generally speaking, we don't know. Practically, we know that it's governed by a linear operator. We know that, but things like misconceptions such as the eigenvalues of this will mean anything. No, they won't in general. And I see so many papers in which people just assume that the eigenvalues of A of t mean something, right? It turns out if A of t is very slowly varying, then they almost mean something. Even then, you can, for long enough times, they don't mean only on anything and only on short times. So there's some special cases if, also this A of t is identity plus some tiny matrix which is uniformly bounded in time, then you can make some inferences from the eigenvalues. But generally speaking, the eigenvalues of A of t, and this is one conclusion again to remember, and the eigenvectors, so eigenvalues and eigenvectors of AT have no relevance in general. Specifically for the stability or for the solutions of x equals 0. Because in the homogeneous problem, x equals 0 is always an equilibrium point, and people attempted to work with the eigenvalues of A of t. Okay, no relevance. In general, you can easily construct counterexamples to anything. It may have all negative eigenvalues, negative real parts, and the equilibrium is unstable, or the other way around. All sorts of examples in the literature. Okay, so there's no result like that. So this is the homogeneous part, and we call this the fundamental solution matrix. And these are terms we already used before. That's why I'm just repeating. Fundamental solution matrix. And it has, when you properly normalize it, then it's just the identity at x naught. Okay. And you have that. So it's always guaranteed to exist, but we have no general procedure for constructing it. That's what I'm trying to say. Numerically, your best bet is solving this equation numerically, because there's no other general procedure that would be really workable. There's small, small t expansions and things like that. They're only valid for small, short times. So what about the inhomogeneous part? What do we know about that? Or the inhomogeneous equation? So the general solution to the full problem. So let's call this star of star. There's this classic procedure by which I'm sure many of you have seen, goes by the funny name of variation of constants, which should be a contradiction because by definition constants don't vary, right? Nevertheless, that's the or variations of constants, or sometimes variations of parameters, which again normally don't vary. So you basically look for a general solution. You try to save the knowledge you already have. So instead of saying that x of t, which is now the solution of the full problem, this, right, rather than just the solution of this, rather than saying that it's of this kind of fundamental matrix solution times the initial condition, now you say, okay, I'm going to try the fundamental matrix solution because it's clearly an important entity, but I allow some time-dependent vector there rather than, strictly speaking, the initial condition. And when you plug this into the equation, this is essentially an ansatz. You don't know a priori if this works or not. So you substitute it into star, then you have to differentiate it. So you will be getting phi dot t naught t phi plus, or phi that too, phi dot phi t naught t phi dot, right? Because I just used the product rule when I differentiated this. And on the right-hand side, now you have a times this solution. So a times phi t naught t phi plus you have b of t, because I'm substituting now into the full equation. That's what I've written here. Okay. But remember the definition of phi dot. Phi or phi dot, when you plug it in here, that's just a phi. That's a property of the fundamental matrix solution. The a phi t naught t equals phi dot t naught t. That's just by substitution. You can just plug it into it, and then it's true for any x naught. You will get two operators. Their action on x naught is the same for all choices of x naught. Therefore, the two operators are the same. That's how you conclude this. But if you then conclude that, then the first term becomes, I don't write that out, just in the interest of saving time, all right? So this is equal to just that, right? So this is equal to a phi. So this is a capital phi times little phi. But I already have that on this side as well, a capital phi times little phi. So then those cancel out. Those, okay? So I use double star to infer this cancellation. Did I? Okay, I had one more term. And then what I end up getting is the fundamental matrix solution is always non-singular. That's also a property of that. So I can invert this matrix, and phi dot is therefore phi, and this will be t naught. That's another, that comes from the inverse of phi t naught t is phi t naught. So whatever, if I go from t naught to t forward and I ask what brings me back, then it makes sense just to say, well, it's the same as starting from t naught and flying backwards. Starting from t and flying backwards. That's a property of fundamental matrix solution. Then I apply it to phi. So this then enables me to integrate this. Phi at time t minus phi at t naught equals the integral from t naught to t phi. And now I have to change variables. The integration variable is s. Okay. T naught and then phi s ds. Okay. And of course, the way I've started, I have to respect the initial condition because let's look at what this guy is, the identity at T naught, at T equals T naught, right? So then x at T naught, which is x naught, my initial condition must be equal to phi at T naught. So this must be equal to x naught, which is the initial condition. So from this one, I obtain therefore that phi of t equals x naught plus the integral from T naught to T phi s T naught phi b. That was a b there, sorry. B s ds, right? That was this term coming there from the integration. So that's b s ds. And I'm almost done. I have to scroll down because now I go back and simply I use the ansatz. That's where I started from. So for this choice of phi, the ansatz is satisfied because I plugged in. I said, okay, let's see where I get with the ansatz. Do I get something under which the ansatz is satisfied? And yes, this is what the ansatz implies. So then by the ansatz, I have x of t, and I'm substituting now into this. I'm substituting this expression into what I had there, right? So when I do that, I get x of t equals phi t naught t, first acting on x naught, right? Because I'm plugging this one in place of phi. So then the fundamental matrix solution first multiplies x naught, and then the fundamental matrix solution will multiply this integral. So plus phi t naught t, integral from t naught to t. I have phi from s to t naught, bs ds. Now the good thing is that this doesn't depend on s, it only depends on t naught and t, which from the point of view of integration, both of which are constant. So I can grab this and put it inside, which I can, then these two matrices will multiply each other. And then I use this group property of the fundamental matrix solution, which we mentioned earlier. Namely, if I go from S to T naught, okay, so I apply the fundamental matrix solution to something. Think of this as an initial condition, taking you from S to T naught. And then I evolve under the fundamental matrix solution from T naught to T. That's just the same as evolving from S to T to begin with, because these two times are the same. So that's just the group property of the fundamental matrix solution, which is your expectation that you would have for determinism, right? If you ask that the solution, how do solutions of these differential equations, is really a dynamical system? Does the presence uniquely define the future? If so, then, okay, I evolve from this initial condition to this point. Okay, I stop there. Then I evolve from this initial condition to another point. Okay, stop there. Now, could I have evolved in one shot to that point using the same solution operator? Yeah, there was no need to stop. So this one from here to there, it was phi from, T naught to an intermediate time, and then from the intermediate to a finite time, there was another phi from intermediate to finite, but that's just the same as taking phi from the initial time to the finite. That would be one of the group properties that this fundamental matrix solution satisfied. So I then simply concatenate these two. I bring in the other one into the integral sign. That gives me phi t naught t x naught plus the integral from t naught t. And now I concatenate them from s to t, bs ds. And there are various names to this. I think a classical name is the Duhamel integral. And I think that's how it's sometimes called, say, in mechanics literature. This is just a general solution of the inhomogeneous problem. Of what was my of star? So in principle, once you know the the solution of the homogeneous part, then you know pretty much everything modulo an integration, because you can use it to solve the inhomogeneous problem. This is where the initial condition appears. Okay, so this will be the homogeneous solution as we are used to from the theory of linear systems. So this is the X homogeneous T, which already satisfies the initial value problem. And this is the X particular solution. Except that you don't have to experiment, as we sometimes teach in ODEs, as that try this, try that. This is always a foolproof recipe. If you know the fundamental matrix solution of the linear part, you don't have to do trial solutions and this and that. This will be a particular solution. And it also tells you, shows you that whatever the stability property of the origin was in the linear system, which was basically governed by this linear operator, whether it had, you know, whether it was shrinking X naught or it was growing X naught and so on, that same exact stability type will be true for the particular solution, because your particular solution is ticking by itself. It doesn't know anything about the initial condition. It couldn't care less. It's a distinguished solution. And with your full solution, you're off that typically to what extent is governed by the initial condition that you pick. Now, suppose that your X equals 0 was an asymptotically stable equilibrium position for the homogeneous system. That means that this operator is shrinking all initial conditions, okay, in the homogeneous problem. Now it will do, look at this part, it will do exactly the same, but when it shrinks all those initial conditions, instead of forcing you to 0, now it forces you to converge on this one. So this particular solution is everybody's target in the end, in the case when the original X naught equals 0 was asymptotically stable. Now, what does that depend on? Just for a quick discussion, how will I know that this operator is shrinking over X naughts? Okay, the appropriate notion for that is the singular values of that operator. So it's the singular values of the operator that govern that type of behavior. Okay, and if they are less than 1, those are positive numbers, then this operator is shrinking all distances. If there are some which are bigger than 1, then there will be distances that this operator is growing. Okay, so let me just spell some of this out. So the stability of X equals 0 in the homogeneous system part is equivalent to the stability of X part T as a solution in the full linear system, which has the inhomogeneous part as well. So the full linear system, what did I call it? Yeah, star. Okay, and it's determined, both are determined by the singular values okay. Why? Why not the eigenvalues? Right. Well, it's the singular values because you're fundamentally are interested in the homogeneous case. But since the two are equivalent, let's just talk about that. Right, and what you're interested in is the norm of X of T, right? Or equivalently the norm squared. What does it do? Does it go to 0? Does it grow? And again, we've done estimates like this, but you don't even have to do the estimates now. Just use the fact that we know that the solution is governed by the fundamental matrix solution. So I can calculate this norm squared by taking just the inner product of x of t. These are individually x of t, right, by itself. Okay, so this is so let's not postulate eigenvalues, eigenvectors, and whatnot. This is what I'm interested in. And then using the fact that this is an n by n matrix, sorry, and this is an inner product, then this will be the same as the inner product of x naught with the transpose of t naught. Take the operator and take its transpose. And this is the same calculation that came in the case of finite time Yapurov exponents, because the two are related. It was the same calculation, but this is now slightly different context, but same calculation. So the relationship would be for a general flow when we calculate the Yapurov exponents, that this will be the deformation gradient, but it would play the same role, basically the derivative of the flow map. Here, the derivative of the flow map is the full map that you see here. Its derivative is Jacobian, is just this. Okay, that's why when you look at finite time Yapurov exponents, when we were investigating very similar questions, how the solutions grow, perturbations of the solutions grow and decay, then we were getting very similar expressions. So here's the thing. So this was called the Cauchy-Green strain tensor, generally speaking. And the eigenvalues of this one will determine the behavior of this quadratic form. This is positive definite. And if all its eigenvalues are less than 0, then no matter where you place x naught, this will be shrinking, this value. If some of them are larger than 1, then it will grow. But the eigenvalues of t naught, okay, are equal to the squared singular values by definition. Of the deformation gradient. So that's why it's at this point, it wasn't the eigenvalues of the deformation gradient that mattered. But once I formulate the problem like this and I get to a quadratic form, I'm on familiar grounds from linear algebra, then I can talk about the eigenvalues of this matrix, because that they will decide for this, they're always real, whether I will be this norm will be growing or shrinking, but then this is their connection with the singular values of t naught t. Okay. So I have to stop. Oops, sorry, I'm over time and I still didn't cover what I wanted to cover. So tomorrow I'll make a heroic attempt to finish time-dependent linear systems. Maybe some of it I will just scrolling through rather than writing out, and that's where I'll end the semester. Okay, any quick questions?
I do have one quick question.
Yeah.
Yes, when we were speaking about the perturbations for 1 degree of freedom systems, and we mentioned that these perturbations cause deformations in the potential energy. So I imagined
which was where? Here. Okay.
Yes. Okay. So I'm also imagining a 1 degree of freedom system, which is a lumped mass, maybe connected with a spring, and the perturbation is to the mass and not to the K of the spring, maybe. So in this case, V doesn't deform, V stays the same. So this means also that the heteroclinic orbits will be robust, since the perturbation doesn't lead to deformations in V, and it stays.
I mean, if V remains the same, right? And then what are the perturbations then you have in mind? So V remains the same?
And the mass maybe changes. There is some uncertainty in the lumped mass that I am putting.
Okay, as long as the mass doesn't depend on the position, right? Because then the mass is just a parameter. And when you go back to what really mattered in constructing the trajectories was this relationship, is that x dot was plus minus 2 over m, what was it? Energy minus v, right? If this parameter was always immaterial. If I tinker with x, m, it doesn't really matter in terms of the outcome, okay? as long as this is the same. But if M depends on X, that's a slightly different thing.
Okay.
Okay. We didn't actually talk about systems like that. We always assume that this is a fixed parameter. But back to your question, if you're really just changing the mass, but not the potential, then, or even if you change the potential, but somehow you have a symmetry that keeps those two peaks on the same level, okay, which we talked about in the case of the pendulum, right? That by construction, by the definition of that coordinate, one must preserve that symmetry, then yes, the heteroclinic orbit will be structurally stable. If it's connected to a hyperbolic fixed point, right? Because there are cases in which something looks like a hyperbolic fixed point, right? But this could be on a center manifold. So suppose I linearize and I get nothing, just two double zeros, and I start adding the nonlinear terms, and the nonlinear terms introduce these stable and unstable manifolds. It's possible, okay? That means that at linear level, the eigenvalues were actually 0, and therefore this fixed point is not structurally stable. It can be destroyed, okay? So just because, not that these happen a lot, but they could happen, right? So the precise statement is that that homoclinic orbits and attached to hyperbolic fixed points are structurally stable, and heteroclinic orbits under symmetry attached to hyperbolic fixed points are structurally stable.
Thanks.
You're welcome. Anything else? Done? Okay. See you tomorrow. Have a good evening.